So this video is about formula writing. So the definition it gives in the book is to first write the symbol of the cation and the anion, and then add subscripts as needed to balance the charges. So now it sounds really complicated, but it's not. Here, let's start with a simple example. So you have lead 2 chloride. So you're going to start by writing the symbol of lead, which is just Pb, and the symbol of chloride, which is Cl. And then you write the charges. We know the charge of lead because it's lead 2, so the charge is going to be plus 2. And the charge of chloride can be found on the periodic table. It's just minus 1. So now, in order to know which subscripts you need, you just do crisscrossing. So you take the charge of Pb and move it over to Cl, and the charge of Cl move over to Pb. So now the subscripts that you have are Pb1, Cl2. Now you really don't need to write the 1 there. You just need to write the 2. So now you know that the formula of lead 2 chloride is PbCl2. Another way to think about this is if you know that the charge of Pb is plus 2 and the charge of Cl is minus 1, then you need to balance the charges. So you need to have 2 Cl's for every 1 Pb. So you add 2 into the subscript of Cl to show that you have 2 Cl's. Alright, now another example. This one's a little bit more challenging, but just start with writing the symbols. So the symbol for iron is Fe, and the symbol for oxide is just O. Now, since you have iron 3, you know the charge for Fe is just plus 3, and the charge for oxide, which can be found on the periodic table, is minus 2. Now, again, we can just crisscross, so you have Fe2, which is the charge for oxide, and O3, the charge for iron. So now we have Fe2O3, which also, looking at the charges, we can see that the charge for oxide is now minus 6, and the charge for Fe is now also plus 6. So we know that the charges are balanced, meaning that we know that's a correct formula. Now one last example, we have tin 4 oxide. This one's a little bit different, but here, let's just start with writing the symbol. So for tin, it's going to be Sn, and for oxide, it's O. Now, the charge for Sn, since it's tin 4, it's going to be plus 4. And the charge for oxide is, again, minus 2. So now, when we do crisscross method, we have Sn2O4. But these can both be reduced since they're both factors of 2. So we can reduce these and get Sn1O2, which can just be written as SnO2. Another way to think about this is for every 1 Sn, we need 2 O's to balance the charges. So now we have a plus 4 charge here and a minus 4 charge here, meaning that our charges are balanced. Okay, so now we're doing polyatomic ions, which are slightly more tricky, but it's okay. So the definition it gives in the book is first write the symbol or formula for the cation, then write the symbol or formula for the anion, and then add subscripts as needed to balance the charges. And whenever more than one polyatomic ion is needed to balance the charges in an ionic compound, use parentheses to set off the polyatomic charges in an ionic compound. Now again, that sounds really complicated, but it's pretty simple and it's very similar to binary ionic compounds. So, for example, let's start with magnesium nitrate, a simple example. So once again, we start with writing the symbol for magnesium, that's just Mg. And for nitrate, that's NO3. Now, the charge for Mg is plus 2, which can be found on the periodic table. And for NO3, it's minus 1. Now, we can do the same method of crisscrossing as we were doing before. So we have Mg1, which we don't have to write. Now, NO3 is a little bit trickier. We have to use parentheses to set it off. So NO3, use parentheses with a 2. Now we see that Mg, NO3 taken twice. So now another example, which is also a little bit trickier, is iron 3 sulfate. So now we start with writing the symbols as usual, and the symbol for iron is still Fe, and for sulfate it's SO4. Now the charge for Fe3, since iron 3, the charge is just +3, and for sulfate, the charge is -2. Now we do the same thing that we did with the binary ionic compounds, and we just crisscross once again. So we get Fe2 and use parentheses, so we get SO4 taken 3 times, since we get the 3 from the charge up here. So we have one last example, which is a little bit different again. So it's lead 4 carbonate. So now, once again, we start with writing the symbols. So for lead, it's Pb. And for carbonate, it's CO3. Now, since it's lead 4, we know that the charge for Pb is +4, and the charge for carbonate is -2. So now we can just do crisscross to get the subscripts. So we get Pb2 from up here, and parentheses CO3, close parentheses, 4, right here. Now, once again, like we had to do with the binary ionic compounds, we have to reduce. So we reduce that, and we get PbCO3 taken twice. Alright, so now we're doing binary molecular compounds. Now the definition it gives in the book is, first, use the prefixes in the name to tell you the subscripts of each element in the formula. Then, write the correct symbols for the 2 elements with the appropriate subscripts. Now, let's start with an example. So first, dihydrogen monoxide, which sounds really complicated, but actually it's just water. Now, you can tell this by, like it said, now the prefixes. So, for example, for dihydrogen, the prefix is di, which we know means 2. So that means there are 2 hydrogens, so 2 H's. And monoxide, mono, means 1. So that means there is 1 oxide. So when we put it together, we get H2O, which we know is just water. One of the most important things about making binary molecular formulas is remembering all of the prefixes. Now, they're not too difficult if you just think about like shapes. So for example, mono means 1, di, 2, tri, 3, tetra, 4, penta, 5. For example, think of a pentagon, and a tri, think of tricycle. Hexa, 6, like a hexagon. Hepta, 7, like a heptagon. Octa, 8, like an octagon or an octopus. Nona, 9, and deca, 10. Now, there is a lot of them, and they're on page 281 in your book. Now, there is a lot of them. But they're pretty easy to remember if you just think of the shapes and, just remember them. But they are important to know because you need to be able, when given a name of a binary molecular compound, you need to know the prefixes will tell you what subscripts you need to use. So you need to memorize them to know which subscripts. For example, if you have monoxide, that means you have 1 oxide. Or dioxide, for example, carbon dioxide, that's carbon plus 2 oxides, so CO2. And it goes on, so if you have tri in the prefix, then you know the subscript is going to be 3. The second example is dinitrogen tetroxide. So first, we look at the prefixes. So we have di, meaning 2, and nitrogen, so we have N, 2 nitrogens, and tetra, meaning 4, and oxide, the symbol for which is O, so we have O, 4. So now our formula is N2O4. And now doing phosphorus pentachloride. Now, since there's no prefix in front of phosphorus, we just have 1. And the symbol for phosphorus is just P, so it's just 1P. And now pentachloride meaning 5 chloride, and the symbol for chloride is Cl. Penta meaning 5, Cl, 5. So now our formula for phosphorus pentachloride is PCl5. And now, moving on to acids. Acids are a little bit different. So now if the name if the name of the acid ends in ic, then that means that the ion that it came from has to end in ate, A-T-E. And if the name ends in us, O-U-S, then it has to come from an ion that ends in I-T-E. Now, a way to remember that is you ate something icky, so you remember that ate goes with ick, and you bite into something gross. So you remember that ite goes with us. For example, we have sulfuric acid. So now by the suffix ic, we know that it came from the ion sulfate, from the polyatomic ion sulfate, which we know is SO4. But acids always start with hydrogen, so we always need to write an H. But then we need to balance it, like we do for our ionic compounds. So hydrogen is always +1, and sulfate, we know, is -2. So then in order to balance the two charges, we have H2SO4. An example is nitrous acid. Now because of the suffix us, we know that it had to come from a nitrite ion, which is NO2. Now we need to have an H in front because acids always start with hydrogen, and because the charge for hydrogen is +1 and the charge for the nitrite ion is -1, the two charges are already balanced. We don't need any subscripts, so it means our formula is just HNO2.